Alright, so I'm going to go over the solution to the infinite potential well. Basically verbatim from Griffiths, but I don't think he invented this problem, so I think that's fair. Yeah, this is a good problem because it's, well, besides being like the first real introductory problem to in quantum mechanics, it has a lot of the important features of quantum mechanics, such as quantization and from boundary conditions. Yet the math is relatively straightforward, so it makes a good introductory problem to the subject. So just to give the setup, we are going to solve the Schrodinger equation, the time independent Schrodinger equation, H psi equals E psi for a particle with some kinetic energy and a potential energy, V of x. And in quantum mechanics, of course, we promote everything to an operator, because the V hat of x hat. And P hat is minus I h bar del by del x squared, del by del x. So H is minus h bar squared over 2m del squared by del x squared, plus V of x, which I haven't specified yet, but the infinite potential well, i.e. a particle in a box, you have some x-axis here, let this be my 0, let the box be of width a, and what I'm plotting here is my potential function V of x, and the idea is that it's basically a free particle in this inner region, but it's enclosed by walls that are infinitely high potential, so the particle basically has no chance of being there. So this is like at infinity over here. So yeah, that's basically the setup. We can write down the potential more mathematically as V of x is 0 within the region 0 less than x less than a, and infinity otherwise. And then I'll just keep this as V of x, with that being the definition. And our task is basically to solve the Schrodinger equation subject to this potential. So let's start in the simple region where the potential is just 0, so in region 1. So our Schrodinger equation reads, of course this is a function of x, that's what we're interested in. So we have minus h bar squared over 2m del squared by del x squared psi plus v of x psi, but remember we're putting ourselves in the middle region here where the potential is 0, so v is 0 there, so we can just get rid of that term. So we just have this simple second order differential equation for the wave function psi that we need to solve. So let me just quickly do a little rearranging, and I get minus 2me over h bar squared psi of x. And let's collect these coefficients into a constant that I'll call k squared actually. Sorry, this should be del squared by del x squared. Again. Alright, so what we have is just a simple second order differential equation for the wave function, and we know the solution to this. What functions do we know that when we take two derivatives we get the same function back up to a constant and a minus sign? Well, these are just the trigonometric functions. So we can write the general solution to this differential equation as some coefficient a times sine of kx plus some yet to be determined coefficient b cos kx. And you can verify that if you take two derivatives of this function, you'll get the same thing back, but with the coefficient of minus k squared out front, right? Because two derivatives of this, I get a sine. Each time I get a k out, and a minus as well. So this is our wave function, general solution to middle region. Now let's think about the other regions, regions 2 and 3. And just to jump to to make a long story short, these outer regions are basically going to amount to our boundary conditions that allow us to determine the coefficients a and b in this wave function. So we really don't have to do much work here in terms of solving for the wave function in these regions, because we're by construction saying that the potential in these regions is infinite, and so the particle has no chance of being there. It's like classically, what is the probability of finding a particle outside of a box with infinitely high walls? Even in quantum mechanics, where we have tunneling allowed, if the potential is infinite, then the probability of finding the particle there is still 0. So we can just immediately write down that the wave function in these regions is 0. But the reason this is important is because we want our wave function to be continuous in space, which means that basically whatever our solution is in this region, that's what we're looking for. Let's say it's some, I don't know, some squiggly thing like this. I'm not saying that is the solution. That's what we're after here. But whatever it happens to be, it better go to 0 at the boundaries of this region, such that it smoothly transitions into 0 in the regions where the potential is infinite. So effectively, the fact that the wave function has to go to 0 in these infinite regions tells us what our boundary conditions are for this wave function in the within the box, in a region where the wave function is non-zero. So mathematically, we have that these essentially are amounting to our boundary conditions. Psi of x equals 0 must vanish, and similarly psi of x equal to a must vanish. So let's start with the first one here. If I plug in x equals 0 into our wave function, I get psi of 0 is a times sine of 0, which is 0, plus b times cosine of 0, which is b times 1. So psi of 0 is b, but by the first boundary condition, this thing has to vanish. So what we've concluded is that this coefficient b is 0. All right, that's nice. The next thing, let's try the other one. So psi of a, if I plug in, remember, b is already 0, so we only have this piece left. We have a times sine of k times a. And this also has to vanish. Now, we have a couple of options here. First thing that could happen is that the coefficient up front, a, vanishes. But if that happens, then the wave function is just 0, which is not just boring, it's actually a problem because it can't be normalized. Remember, the wave function has to, when integrated over all of space, give a probability of 1. If the wave function is 0 everywhere, there's no way it could have, there's no way it can integrate to 1, and there's no way, in other words, to normalize it. So the a equals 0 option is no good. So what we're left with is trying to satisfy this constraint by tuning the argument of the sine function. So remember, sine of x, sine of some function x goes to 0 when x is some integer multiple of pi. So essentially what this condition is telling us is that we have k times a must equal n times pi, where n is some integer. So let's think a little bit more about what this is telling us. So remember, k is defined as, it's related to these coefficients here. So let me plug those back in and see what we find. So if I substitute back in my expression for k, I have 2me over h bar, that's k, times a is n pi. And if I just square both sides and rearrange for e, I obtain my energy eigenvalues. Remember, n is an integer. So the point is here that what we've determined is that the energy eigenvalues for our time independent Schrodinger equation are quantized in square integer multiples of the rest of these coefficients here. And remember that how we got here is basically just by imposing boundary conditions. So the moral of the story is that quantization in quantum mechanics comes from boundary conditions. The last thing to do, so we still haven't determined A. We know what K is, we know it's some integer multiple of pi. The energy is the following, or is what I've written there, but we still haven't determined A. But we can actually figure out what A is just by imposing normalization of the wave function. So we know that psi of x squared must integrate to 1. We integrate over all of space. Wave function 0 here, so we can just focus on the region between 0 and a, where we know what the wave function looks like. Remember, b we found to be 0 already. So we just have something like psi star of x, psi have a squared sine squared of kx. My normalization coefficient just comes out. Sine squared kx dx. And I believe that this integral just evaluates to a over 2. I hope. I forget. But it's something like that. But anyway, if we trust that result, then we can rearrange and solve for our normalization coefficient. So we basically conclude that a squared is 2 over a. And so a is at least up to a complex phase factor is given by the square root of 2 over a. So we can finally write down the normalized form of our wave function, i.e. the solution to the time-independent Schrodinger equation, and we find that it's 2 over a sine of kx. And let's perhaps we can do a bit better if we just write this in the form shown here, right? K has to be n times pi over a. So we could write this like this. And so now we observe that our wave functions are actually indexed by this index n. So we might write that the nth solution to the Schrodinger equation is given by this wave function here, and the energy corresponding to each of these wave functions will also carry an index, and the energy is determined by that index. And this is basically the set of solutions to the time-independent Schrodinger equation for the infinite potential well. The point is that there are an infinite number of solutions that satisfy this equation here. And we've found that we could index them with a variable n, with an integer n. And physically, what these solutions look like is they're just sine waves. But if I draw a few of them, you can get a sense of what they look like. So for example, the n equals first solution it's just like a wave like this, standing wave like this. The next solution will have, so this has like 0 nodes, the next one will have 1 node, so it'll be something like this, n equals 1, n equals 2, and so on. And so in principle, just like from classical mechanics where you have like masses oscillating on springs, the eigenvalues of those equations of motion, those eigenvectors, can be added in linear combinations to construct any sort of motion that you could think of. And similarly, in this case, any sort of general solution, any general type of motion or wave function that we could think of could be constructed. Maybe I'll call this like phi of x. It's constructed from some linear combination of these eigenmodes psi n of x. And if we wish to allow for these solutions to be time dependent, then the time dependent Schrodinger equation tells us the rule for constructing those solutions. It's basically just to tack on a factor of I, E, and T over H bar. And so this represents the solution to the time-dependent Schrodinger equation for the infinite potential well, and the initial conditions, or whatever the initial state of the system is, comes down to specifying what these coefficients are initially. So for example, if we wanted to put the system in an eigenstate, in the n equals 1 state, we would set all of these alphas to 0, except for the one corresponding to n equals 1, and then the system would remain in this state, and then we just evolve according to the time-dependent Schrodinger equation by accumulating this phase, e to the I, n equals 1, energy T over H bar. And so yeah, that's the infinite potential well.